All right, we're back in action and we're diving back into complex numbers. I've got a little program planned out for today. Last time we wrapped up by jotting down some exercises. I'll start off by solving those for you. And then we need to review what does it actually mean to take the square root of a complex number and how do we interpret that geometrically. This is indeed one of your oral exam questions, so we need to make sure we've gone over it a few times. We'll practice it in pairs later, and then I'll show you something I won't hold you accountable for in the oral exam, but it's pretty cool that you've seen it. And if you get the hang of it, feel free to mention it during your exam. But it is about how you take the square root of a complex number when it's in rectangular form rather than polar form. Indeed, that can be done as well. I've prepared a little derivation that I want to show you about how to do that. But as I mentioned, it's not something I'll just pop a question about during the oral exam and say, could you please demonstrate that? So we're exploring this out of pure mathematical curiosity, that bit there. And then there's the complex conjugate root equation, which is also part of one of your oral exam questions, so we need to cover that. And finally, there's something called de Moivre's theorem, and I believe that's how you pronounce it, de Moivre's theorem. Some say de Moivre's or something like that, but it's de Moivre's theorem. It's actually a clever formula that can be demonstrated with complex numbers and can be applied to all sorts of clever, real, that is non-complex problems. Does anyone have the assignments from last time in front of you? Who could read the first one out loud? Yeah, you've got it there. It says to rewrite in rectangular form.
Was that the first byte? There was a task before that one too.
That was the first one, marked with a B there. That one, yes. So let's just quickly work through a couple of them. Let's look at problem 1. It looks like this. It's written in polar form using Euler's notation. When you choose the principal argument, we have a complex number denoted as c equal to 3 plus 4i. We have a complex number on a rectangular grid. And when we plot it, we'll notice that it's located in the first quadrant of the graphing plane. So here's the real axis, and here's the imaginary axis. And then we'll place 3 units out along the x-axis and 4 units up here. So let's say that's 4 there. So our complex number is located right there. It's right there. Our task is to describe the detail in polar form. So we draw a straight connection line and the distance out to z. The length of that line is what we call the modulus of z. And then we need to calculate the angle that lies here, which I can call theta. Let's start by trying to find the modulus of z. We've learned that we do this by taking the square root of the real part of z,
square plus c plus the imaginary parts.
Ready, set, 1. And remember, the imaginary part of z is a real number. You don't include the I. So when I plug the numbers in here, I need to say 3, that's the real part, and 4, that's the imaginary part. Then I get the square root of 3 squared plus 4 squared. And it was designed to result in nice numbers. We get 9 and 16, which is 25, and the square root of that is 5. So now we know that the distance from here to there is 5. Now we'd like to find this angle, and it's really simple because we're in the first quadrant. So we just take the arctangent of the opposite side. That's what we do with the adjacent side. So our angle theta, we find it by taking the arctangent of 4/3.
And if I just do that,
my calculator,
then I'll get it. Maybe I just need to remember to set the calculator to calculate degrees. Menu radians, switch to degrees, and then tangent inverse of 4. 1/4 gives 53.3.
And now I can jot down my result, seeing as I have both the modulus and the argument right there. Is that a principal argument?
Yes, because it lies between negative 180 and positive 180 degrees, and that's the main argument. So I could theoretically write the setup.
I can express z as 5 times Euler's number raised to the power of the imaginary unit I times this angle here, 53.13. Finish the first task. And then I just need to adjust to log into this smart device. Everyone will soon go digital. Except for Benjamin Grigg. It's still old school. Now let's take an example of one where you need to do just the opposite. Now you have to convert to rectangular form from polar form. So this task is called task 6. Here we have a complex number which is called z equals 5 anyway. Complex all its numbers and others.
Then you manage to lift 10 times.
If we were to start by plotting that onto the complex plane, so what can I say right off the bat when I click on the number? All right, I can say that the complex number set over there is currently at a distance of 5 units away, and then it's rotated up to the angle that comes after the eye. So basically, when you look at a complex number like this, you almost completely ignore the eye glazing stuff. It's just part of the notation you get used to. Your eye scans here and there, and there's the information. So the number is currently 5 units away, and it's rotated at an angle of pi quarters radians. And we must remember that 360 degrees is a full turn around in a circle, which corresponds to 2 pi radians. So it must be that pi radians is equivalent to 180 degrees, half pi is 90 degrees, and a quarter pi is 45 degrees. So let me jot down here. A quarter pi, that's the same as 45 degrees. And that means I know that my complex number is somewhere on that 45 degree line, and it's at a distance 5 units from the origin. So I just take a compass with the point at the origin, set the compass to 5, and I draw it as a circular arc. And right there, that's where my complex number is located. So now I know where the set is. So I've got it illustrated on the diagram. Now I want to convert it to rectangular form, which means what I want to find out is how far it is right here and how far is it here. If I can figure it out, then I can rewrite it in the rectangular
A
form.
plus IB, which is a rectangular form.
And we learned that a complex number can be written as R, where R stands for the modulus, or the radius of the circle that the number lies on, times the cosine of the angle, plus I times the sine of the angle. And then we can just plug the numbers in. It was modulo z, and modulo z can be read as 5. So this should be a 5 times the cosine of the angle, which is pi over 4. And then we can continue calculating that. If you're not sure, you can always punch into a calculator what cosine of pi over 4 is. It's the same as asking what's the cosine of this angle at 45 degrees, and that gives you square root of 2 over 2 if you ask the calculator. So this gives square root of 2 over 2. And because the angle is 45 degrees, this also gives root of 2 over 2. Because sine of 45 degrees is the same as cosine of 45 degrees. So that's also root of 2 over 2. So now I can just multiply by 5. So I get square of the gang 2.5 plus 5. Square root of 2.5 plus 5 times the square root of 2.5. You better write that down uniformly. Square root of 2.5. And then you can't. So this right here is the real part, and that's the imaginary part. And now it's in proper correct form. And of course, if you were a physicist, you could translate this into a decimal. But mathematicians do it better because it's in exact form. You could run into trouble if you hand this over to a contractor, you won't get a pass. If you tell them you need so many liters of paint or something, remember, if you're going to use it one day, convert it to decimal numbers. But in mathematics, we just deliver the exact value. Did you have any questions? It's fine if you just calculate this on a calculator if that's what you're asking about.
Yes, you can do that too, yes.
So it states that we need to determine both square roots of, and then let's take, for example, exercise 9. Here we have a complex number called W
Equals 16.
raise Euler's number to the power of 3p over 4. And we need to find both of the complex square roots that exist for that number. So we should start by asking ourselves, where is w located? Let's try to draw it. First off, we can see that w is the complex number that's at a distance of 16 units from the origin. So you should imagine that I'm drawing a circle with its center at Orico, which has a radius of 16. So somewhere on this circle I'm drawing right now, that's where the double phi is located. Somewhere on this circle. And up here we can see what the angle is. To understand 3pi4, you start by understanding pi4, which we did over here. Pi4 is 45 degrees, and I have 3 of those, so I just say 45 degrees plus 45 degrees plus 45 degrees. This means that I am at an angle of 135 degrees, also called 3pi4. So here lies my double angle, and I'd like to find the two complex square roots of that number. Last time we saw that what you need to do is take the angle and then halve it. So half of 3 pi quarters must be 3 pi eighths of the way. So we can use this formula, 1 square root of w.
It's the square root of 16.
Take Euler's number decomposed into multiplication, and then I have to halve this angle to get 3 arrows properly. And we can write that a bit more elegantly because the square is 16, which is just 4. So we can write it as 4e3p8. So that means one of the square threads is on a circle with a radius of 4, rotated at an angle that's half the size of that one. That means it's half of 135 degrees.
And it's probably about here, give or take.
So it would have been there if it needed a power of 16, but it needs a power of 4. So I've got to halve that, bringing it down to 8, and halve it once more. So my coil wire is actually located around here somewhere. So look at this little circle here, the one I'm drawing now,
Who has a radio chair?
a radius of 4. Well, the square threads are located, and one square thread lies here, and that's the one. And that square root over there lies in the first quadrant. And if it is either in the first or second square root, then it's in the first quadrant.
Fourth. So we call it the principal.
So all the principal square wires are located over here to the right, and the negative version of the principals are over to the left. And we saw last time that you have to find the negative version of the principal square wire. Well, you'd simply add pi. So that must be 4 times e to the power of I times 3 pi over 8. And then add p. And then you better put them in brackets to multiply through by the whole angle. This means that the other square row lies just a quick sweep over here on the other side, where I've added an arrow, so adding 180 degrees. And so here lies the second one. So this square here, that's the principal one, eh? I could call that the positive square root of w. And this one here, that's the negative square root of w.
So that's one way to do it. Any questions on this?
So you can see that complex numbers can be used to understand operations in 2 dimensions. What can one do with the plane? One can stretch, compress, and rotate. And that's what can be done on the plane, and that's what complex numbers do for you. It's so wonderful. Oh yes, so that was the tablet. Let's quickly review the complex square. As if you were in an exam, what could one say if that came up in the exam? If you're incredibly lucky and you get that question and have to talk about the complex square root, then you could say something similar to what I'm doing now. And of course, you have to expect that you'll be asked some questions, right? But it definitely helps to prepare. What did you hear last time? What you heard last time was that we have some number w, which we know, and we are looking for all the complex numbers z. that we don't know, which when squared will give w. So what do we mean by the square root of w? It's any number that when squared equals w. So what do we mean when we say the square root of 25? We mean any number that when squared equals 25. And there are two numbers that when squared give 25, namely both 5 and -5. And that's why they say the number 25 has two square roots.
And
Similarly,
then w, if w is
next
complete,
number
has two square threads.
Exactly, unless w is 0, in that case it only has one square root. And that's why one might stress that w is not 0. And it's quite fantastic if it's 0. Then you're done right away. So it's said that I'm assuming I have a known complex number that is not 0. Now I'd like to show where to find the exact two square roots that exist. And one should also assume that w is written in some clever form. And the cleverest form is Euler's polar form. So here we have a known complex number with a known modulus and a known argument. And they have made sure to represent the principal value, which is the principal argument. And that lies between -pi and pi. Minus pi is not included in the interval, but pi is. So if you have a complex number that happens to be a negative real number, what's the angle? If it's going to be a principal angle, then the angle is. So any negative real number is also a complex number that just has an argument of exactly pi.
That's exactly why this number here is the best.
It's a really beautiful number because how far is this number from 0? Just 1 away. And what's the angle we've rotated through? 180 degrees. But then it's purely negative for real.
So this is the other way you should talk about -1.
So here a minus actually stands for
Shut up.
shorting. And isn't it true that -1 + 1 = 0? So you just take the disguise off of -1 and put it there, and it reads I in pi.
+1 align with 0.
And there you have it, the world's most beautiful formula. And otherwise identity. Well, while I'm back here, I just think of turning it off. The number we need to find is z. And let's say we're looking for z in polar form using Euler's notation. So we write z as some modulus times Euler's number raised to the power of times some angle. And if we are to find z, then we need to find r, and we need to find theta. That's what we're hunting for. And so now I'll take this expression for z and substitute it into z's place, giving us r e to the power of I times theta. Now we must include w with a capital R. And remember, this is supposed to be squared. So it'll be a capital R squared, e to the power of I. And last time we saw how to handle this. You just square the whole thing by squaring each factor individually. So this can be rewritten as r squared times e to the power of I multiplied by 2 theta, because when you square e to the power of I theta, you have to multiply the exponents, as we learned in the rules of exponents.
And on the right side, we still have the large R, E, I, F, I.
And then last time you saw that if we have two complex numbers that need to be equal, well, they have to be equally distant from the origin, and they must have the same argument, except for an integral multiple of 2 pi. That means the angle that points to the numbers must be the same or the same, except for an integral number of full rotations. And this means that I can conclude that what is written here as modulus must equal what is written there as modulus, because everything in front of Euler's number is modulus. So this is the modulus of this complex number, and that is the modulus of that complex number. So we find that two things must be satisfied at the same time, namely r squared must equal big R. And we can quickly wrap that part up, so then we'll know what the little r should be. The little r should be the positive square root of big R. Why does it have to be the positive root? It's a modulus. A modulus cannot be negative because it represents a distance. And distance can't be negative, just as areas can't be either. Do you know anyone who lives in a 2-room apartment of minus 27 square meters? You can't do that, and you can't be 13 meters minus sine away from home. Since r is a modulus, r should be the positive square root, and this is the very ordinary real square root, that the real number for r is a real number over the modulus for w. And we can also conclude that This is the argument of this complex number, and this is the argument of that complex number. So they must be the same, except for an integer, multiple of full rotations. And that means theta must equal phi. How closely? An integer number of times. For a full rotation, it is 2 pi, and p is an integer number of full rotations. How do I ensure that p is an integer? I do that by saying p can only be chosen from the set of integers.
Sarlin, just as we discussed.
And that's when we start by saying, let's try setting p to 0 and see what we get. The simplest value p can take, if p comes from the set of integers, is obviously 0. So if p is 0, that part just goes away, and then I can figure out theta. Then I get the theta corresponding to p being 0. That's why I call it theta 0. So theta 0 must be phi divided by 2. And that's an important point I can underline because I'm going to need it. So this is an angle that gives me a square root of double value.
So I could try setting PE equal to 1.
Which is the first positive whole number. If I do that, it reads 2 times theta. And which theta is that? It's the theta that corresponds to p double prime 1, so I'll call it theta 1. Should be equal to plus 1 times 2 pi, which is just 2 pi.
And now I can isolate theta 1 in it.
So theta 1 must be pi over 2 plus 2 pi over 2. But 2 pi over 2 is just another way to say pi, because 2 cancels out. And I'll just put a pin in this because I'm going to need it. It's actually a second angle formula, which gives another square root in the double angle. And something I also told you last time, if you move on and try with the next value for p, try setting p to 2, which is the next whole number after 1. So we can see that if we set p to 2, we get a 2.
There are 2 ways to get to the second floor.
So we'll have phi plus twice 2p. Now I've put 2 in place of p. And when I then divide that equation by 2, then theta 2 will equal phi. Then the factor of 2 cancels out when I divide by 2. It must be like this, because when I divide by 2, that's what Christian means. It was good that he wasn't quite so sharp. So we can see that if I add a full rotation to pi over 2, what do I get? I get an angle that points to the same place as pi over 2 itself does. So the square root I get from using this angle is the same square root I would get if I used that angle. Therefore, it's not a new square root. It's not a new point on the Gaussian plane. What we can now see is that there aren't any other locations. There are 2 distinct places on the Gauss plane that correspond to the square root of w, and one has the angle 4.5, and the other has the angle 4.5 plus pi. So the conclusion is that my z, which I was looking for, turned out to be 4.
The one set that uses theta 0.
And what we call the principal square root of w, it's the quadratic y of r, because that was the modulus I needed to use, as I've written here. The number Gauss-Oechler raised to the power of I times the half angle phi. This is the next degree.
And the second one, square wire, set 1.
With what we call the negative version of the principal square root. Well, that would be the square root of r again. This is still the modulus, but now the angle is that plus pi. And here stands the other cardinal point. So we see that the 2 square roots of a complex number are always rotated 180 degrees relative to each other, but they're on the same circle. They are equally far from the center. It was good to visit. Any questions about that? Okay, get it down now because we're pausing the recording.
And then we go out and train.
Okay, we're back in action, and you've had some time to practice. Now I'm going to show you the next item on the agenda, which is, can we then derive a formula to find the square root of a complex number when it's in rectangular form? What we just looked at is how to find the square root of a number when it's in polar form using Euler's method to express it. So what we need to imagine again is that we're talking about a number I don't know. And if I square it, it shouldn't equal a number I do know. So if I can find all the numbers that define W, then I have found the square roots of W. But let's now talk about W, which is the known number. Let's say it can be written in this form, A plus IB. So now it's in rectangular form, this complex number that I know. And I'm looking for a number Z that, when squared, gives W. And let's say that Z is also expressed in rectangular form as an unknown X plus I times an unknown Y. So I'm actually looking for X and Y. We need to find X and Y. Because if we found X and Y, then we found C. And if we found C, then we've discovered some numbers that we've firmly established.
And what have we found? The square roots of W.
So how do we go about this? We need to get a bit creative here. First, what we do is we insert this X plus I into a procedure slot over there. They will then write X plus I times Y. If you square it, then you should get W, but W was a plus I times B. And again, throughout the deduction, it's important to keep up and remind yourself that I know A and I know B. What I'm searching for are X and Y. Those are the ones I want to find. This is what we call the square of a binomial, which we've learned about in algebra. What does that give us? It gives the square of the first term plus the square of the second term plus twice the product. So that means if I work this out, it'll look like X squared. So if I square this, which means plus I times Y squared, that of course gives me negative.
Lost the internet connection.
Because I squared equals -1. And then I need the double products. And the double product becomes 2 times X times Y, so 2XY.
And they're getting started with that, so I'll stand by.
And it still needs to equal A plus I times B. And now we can conclude something, because this is a complex number, which has to equal this one, which is also a complex number. And 2 complex numbers can only equal each other if they have the same real part. And then we're dealing with the imaginary I. So everything that comes after the I has to equal everything that comes after the I over here. And everything here that has nothing to do with I's has to match everything there that has nothing to do with I's. So this is another way of saying the same thing, where I said that 2 complex numbers are equal only if they have the same modulus and the same argument, except for an integer multiple of 2p. But here we're saying that 2 complex numbers are only equal if they have the same real part and the same imaginary coefficient. So that means we now derive 2 equations, equation 1 and equation 2. And what does equation 1 say? It says that x squared minus y squared should equal A. So x squared minus y squared must equal A. The first requirement I have is that x squared minus y squared must equal A. And the second requirement is that 2 times x times y must equal B. So how many unknowns are we dealing with here? There are 2 unknowns. I don't know x or y. I have no idea what x or y are. So there are 2 unknowns, but I do know A and I know B because I know W, which is a plus B. So this is what we call 2 equations with 2 unknowns, but it's not particularly straightforward.
What is it really?
This isn't pleasant. It's because there's a square term and because the unknowns are multiplied by each other. Later in this course, we'll encounter some equations that aren't nice. So they're called nonlinear equations. And to solve 2 nonlinear equations with 2 unknowns, you have to be creative. You can't use the tricks that we learn in 2 weeks' time in this course, unfortunately. So someone sat down, got creative, and figured out what I'm about to show you. This isn't something I've just realized. It's someone else's work. I'm merely the humble messenger of this idea. I saw what they did, and I thought it was clever. Why was it clever? Because it worked. So now comes something that just works. Let's see what works. First off, if you look right here, we can immediately draw a conclusion. If B turns out to be a positive number within W, which makes it positive, what can we then say about the signs of X and Y? They must have the same sign, right?
Let's kick it up a notch.
Negative times negative equals positive. So if B is positive, then we know that X and Y must at least have the same sign, because if they had opposite signs, then that would result in a negative. Suddenly feels good to think that we're with us. So just by looking at this formula, I can determine something. If B is greater than 0, then it implies that x and y must at least have the same sign. Here, the same sign, and you can imagine that, just as they're settling down and pondering it for a bit. And I can also see that if b is negative, maybe we should hope. All right, so far so good. Then there was someone who had the great idea to take x squared plus y squared and put all that squared. It's a good idea. So just hang on for a moment and take a look at this great idea. Here comes a great idea. And at first, you can't see why it's a great idea. But then suddenly you discover it. And the thrill of realization hits you. So let's take a look at x squared plus y squared, all squared. What does that give us? Yes, it results in 1 squared plus 2 times 1 times 1. Because it might concern a size of 2. Are you following me? So that gives us x to the 4th, right? Because it's x squared squared. Plus e squared squared, which becomes y to the 4th power. And then you add the double product, which is 2 times that, times that. So you look at it and think, all right, now I know. So let's take a look at this right here. And ask us, what does that give us? Of course, it's not at all random that one decides to look into this, because that's what we had down here, right? X January minus Y January. So someone got the idea to try and see what does it actually give if I square it, which isn't too far-fetched, because this is about square wire, and it's about either squaring it or not doing anything like that, right? So you can see where he's coming from, the guy who did it. Let's just figure this out. What does it give us? It's also the square of a 2-dimensional size, so that gives us the first term squared, which is x to the 4th power, plus the second term squared, which is y to the 4th power. You always square the first term plus the second term squared, but now it's minus twice the product. Minus squared x squared y. So what can I conclude by looking at the two? I can conclude this. X
And plus y in the end.
Italian. What's that the same as? It's almost the same as that one. Take a look. That there is almost the same as this here. So I can write it like this. The difference here is exactly 4x squared y squared. Can you see it? Because if I calculate this part, what will it give us? This here, this gives us that. And if you take this and copy paste it down here instead, what we'll have is x to the 4th plus y to the 4th minus 2x squared y squared plus 4x squared y squared. It amounts to just a single place plus 2x squared y squared. That's what's written there as it was. Can you see it? So that must be equal to this, if I correct with 4x squared y squared, because that's the difference between the two. So let me explain it again. This here, what's it equivalent to? That there. It says so right here. Take all that and insert it right there. So it reads x to the 4th plus y to the 4th minus 2x squared y squared plus 4x squared y squared. That results in the answer, that there was just a plus 2x squared y squared at the end. And that was precisely what was done in that case, which was that one. So it must be correct.
Can you see it?
Okay. So I noticed something. Take a look here. What is x squared minus y squared? I can't see anything other than x squared minus y squared. It's obvious. So here it actually says a squared minus y end. And 4 for x, 4 times x squared y. What is that? It's b squared. So if I set b squared, then I must say it's squared, it's squared, it's squared. So that's 4 times x squared y. So here, there's actually a hidden b. Just relax. We'll be there soon. So it's just a bit of algebra. I'm charging now. Ready? Back in SOC. So I can figure out, if I want to, x squared y squared, just by taking a square of that over there. So what is x squared plus y squared?
It must be the square root of this.
What do you mean by that? So now I know this right here, and then I know this, which I'll just call 1a, since it's similar to 1. So 1 is x squared minus y squared, and 1a is x squared plus y squared, and that results in that over there. What do I get if I add this equation to that equation? And now I take equation 1 and add it to equation 1a. What do I get then if I do that? we're still onto something good here, you know. I want to make sure you don't think I find it all obvious. I also had to work it out myself. If I add this one to that one up there, it says x squared minus y squared, x squared minus y squared. And then I add it to that one, which is x squared minus y squared, plus e squared. So now I've taken the left-hand side and added it to the left-hand side. What should that yield? The right-hand side plus the right-hand side. So that should give the Cardano of A1 plus B1
plus A.
And now you can see something lovely is happening. I wouldn't have been done in like that. So that's why he got the idea, the guy who came up with that. What do I have left then? 1x squared plus another 1x squared. That must be the total. 2 growth hooks. Have we actually forgotten what we're doing? Hopefully not. We need to find x and we need to find y. And we have determined that it's 2x squared. Oh, are you all following along? The quadratic term a squared plus b squared. Plus a. I think I'll find x. I just need to divide the equation by 2 and take a square root. And then, how many possibilities are there for x? 2. Exactly, plus or minus the square root. So if I just read x here, then I get that x is the positive or negative square root of x. All of this divided by 2. Just stay calm because there's a square root and another square root. It's not so bad after all when you think about it, right? Is this difficult? No, calculate the innermost first. Square root of 16, that gives you 4. And square root of 4, that gives you 2. So it's not just because there are 2 square roots. So it'll be the square root of a squared. Remember b squared plus a now.
All that should have divided us.
So there were the 2 possibilities for x. Now I found x. Expressed by whom? The ones I knew well, a and b. That were the ones that were in w. So now I need to find y. And that's why it was a good idea not to add these 2 lines here together, but to subtract them from one another. So if now I say this one minus that one, so line 1 minus line 1, we'll do that right over here. So line 1 minus line 1, what does that give us? One of them is called x squared plus y squared.
And from there, I need to pull this.
X squared minus y squared. And what should that equal? It should be equal to the right side of equation 1a, as it was stated here, minus the right side of equation 1, as it stands there. So it's the square root of a squared plus b squared. Minus a. And now you can see, when you cancel out that negative parenthesis, that the x mine cancels out with the negative x mine. So they disappear. Som vi ses x-externe sensationer, negative stoff til sånt. Det må ikke det svenska bara för det. On the right side, we still have the square root of a squared that's in play through minus a. So now I can find y. Just like before, I divide by 2 and take the square root, plus or minus. So now I have that y is plus or minus the square root of a, the square root being a squared plus b squared minus a, all over 2. So now that I've found both x and y,
What have I found then? End of message.
what do I know about that set? I know that it yields a w in the second.
So those
And that's
card
all-
threads from W that I found have to come off.
What? Just a quick reminder here. If b is greater than 0, then x and y need to have the same sign. And if b is less than 0, they should have opposite signs. We need to come up with a clever way to incorporate this into the formula. Now, I'll write down the clever approach, and then I'll explain why it's so clever. So here are the 2 square roots of w. What's that there? Well, it's either plus or minus that, and either plus or minus this times I. So I write plus or minus parenthesis. And what do we have here? It says the square root of a squared plus b squared. Do we recognize that? It was the magnitude of w, because that's w, it's called a plus ib. So modulus w's.
That's the square bridge by an.
You're up again. So that means I can write the formula a bit more elegantly. Whenever I see something like the square root of a squared plus b squared, I just write modulus w instead. So here we should write modulus w. Then there's plus a divided by 2. And now comes the clever part. And then I'll explain it just now. Here's the forecast. Let's put a loop around this, and then I'll explain. What was he up to at the end there? Where is this from?
Right, let's have a look. Where did that come from?
Oh yeah, that's what we got. The square window from.
Modulus of w minus a over 2. That's what's written. Can you see it? For this part right here, it's a neat trick I just came up with, or I didn't actually come up with it. Someone else did. I just particularly forgot. But what's written here, it results in a plus if b is positive, and then it results in a minus if b is negative.
And think
It
carefully
has something
about
to
what
do
we're
with the
offering.
modulus of the number itself. So the numerical value, that's what it means, because it's a real number. So if I write 7 divided by the numerical value of 7, what does that give us? The numerical value of 7 is 7, and 7 over 7 is 1, with a plus on it. But if it had said minus 7,
Divided by the numerical value is negative 7.
so this part still gives us negative 7, but this down here still gives 7. So now it cancels out. So now it results in negative 1. So now you can see I've done something quite clever here, making sure I've done something quite clever. If b is negative, then we'll have a minus there. And if there's a minus, then this will have the opposite sign to that. And that's exactly what I concluded over here. That if b is negative, it should have the opposite sign. So if b is negative, then this becomes minus 1. And then that term takes the opposite sign of this one. Can you see that? Oh. So this brings together everything we've concluded into a final formula. And this formula, I am not going to derive it during the oral exam because it gives me a pain in the wrist. But now let's try to use it. So you can see that it actually works. That was the first question, Carsten. And of course, there should be an I here because all of this is Y. And Y should be multiplied by I. So I forgot to write the I. That's absolutely correct. So there should be a plus I here. Multiply that, yes. Otherwise, everything would have become totally real, you know. Have I missed anything else? I don't think so. It all seems accurate so far. But thanks for bringing it to my attention. Any questions about the story? You can see a discharge like this one. It requires,
one is well versed in algebra.
when you're working on the second derivation that we just practiced, it obviously requires a better understanding of how to draw it. That's why I prefer working in polar coordinates. You can directly say it's the semi-angle, square it in the modulus, add 180 degrees to that, and then you have both square roots ready to go. And at this point, you're actually applying quite an obscure formula. And then you end up with the square root of some square root and stuff like that. It's just not as neat to calculate with square roots in the true angular form. It's just not. But it can be done. And if you've got a calculation program like Mabel or a pocket calculator, you can just punch in the numbers and it'll do all the math for you. Shall we give it a try? Finally, we're taking a break. Let's see if we can figure out how to use that formula. So if anyone needs a picture, now is the time before I erase the left side. So if we just leave the formula as it is, So that makes 4. All right, let's try to work this out. I'm just going to make up some number off the top of my head. So the result might not be very pretty, but if you like math, everything looks beautiful. Now let's try to come up with a W.
That means I've got a double Twitter account.
It's 3 plus 4i. We've actually used that a few times. It's that 3, 4, 5 trick there.
Let's say I want to find the 2 square roots.
I'd like to use that formula down there. So looking at the formula down here, I can see that I need to find the modulus of W. Let's start
That's
with that.
not okay.
As the modulus of W. That was just the square root of 3 squared plus 4 squared. So far, so good. And we know that gives us 5 because we've calculated that a few times.
That was a close call.
And then it's just a matter of trying to plug it into the formula. What are the 2 square roots of W? It becomes plus or minus open parentheses.
What are you dragging around, huh?
And then I have to take the modulus of W, which was 5, and add that on. Let's write 5. And then add A, which is 3, of course. And then I need to divide them by 2. And then I have to write. So they have to calculate this sign. What does B over the normal value of B give? What does 4 over the normal value of 4 give? It just gives a plus 1. So it's just a plus. I don't feel like writing the number, but now I know it's going to be a plus. And then I multiply that by the square root of A. And then I had to take the modulus of W, which was 5. And then I need to subtract 3 and divide by 2. So if we continue calculating that, I get plus or minus. Here it says 4 halves, which is 4. So I can make 4. That is 2. Plus, in here it says 5 minus 3, which is 2. And 2 divided by 2, that is 1. And the square of 1, that's 1. So plus I. So there are the 2 square roots.
Shall we then try to see if it fits?
It looks like we did the math wrong. If that's the case, then square this number. You could, of course, go for the double W.
So let's try once to say 2 plus I and
So it's great to help you.
let's try again. The square of the first term, which is 2 squared, is 4.
The square of the second term, which is I squared, that's negative 1. The double product is that times 2.
It's fine.
So that's 3.
Look at this.
Smack, smack. Those were good enough.
2 plus I equals cardboard.
Why? If you continue with the square, you end up with 3 plus 4i. Isn't that neat? And if you felt like it, you could try writing 2 plus I. Insert it and see what it yields. Yep, it does that too if I say 2 plus I. What is it initially? Well, I can just remove the minus sign from the parentheses, so it becomes 2 minus I.
2, 1.
And then I'd like to try squaring that to see if it gives us negative 3 plus I. So let's try it there. Minus 2 minus I. Squared I, that must be it.
That's because I need to write it in a pedagogical way.
Let's see what we get. That times that is 4, because negative times negative is positive. And that times that is a positive I squared. But I squared is negative 1, so it's negative 1. And then we have this times that, which is plus 2i. And then there's that times that, which is also plus 2i. All in all, I get 3. Let's see. So that's what we were supposed to get. Any questions? So let's see if you can use the formula. I'll write up a couple of exercises so we can practice a bit. And then we'll jump to the next topic, which is the complex approach line. So Alexander, you can essentially just pause it for a moment. Here are 3 problems for now. Determine both square roots of w when w equals 1 plus 2i, or when w equals 6 plus 8i, or when w equals negative 3 minus 4i. We'll calculate these in class. Could you pause for a moment? We're ready. Let's work out the problems on the board. So we need to find both square roots of w for these cases. So what we need to do is simply plug into that formula there. And we can just try that. I reckon we'll just solve the first one. And the other 2 will be done in the same way. All right, for problem 1, it says w is 1 plus 2i. So the first thing I need to find is the modulus of w, which I'm going to need for the formula down here. Which means we're looking at the square root of the real part squared plus the imaginary part squared. In other words, 1 squared plus 2 squared. And that gives us 4 plus 1, which is 5. So the square root is 5. So now we can find the 2 square roots of w. I plug it into this formula. So it becomes plus or minus, open parenthesis, the square root of.
And so the model has moved on to square 5.
And then plus a, and a was 1, of course.
And plus 1. And then we divide by 2. Plus the imaginary unit times b divided by the modulus of b. Or the numeric value of b, I should say, since it's a real number. So 2 over the numeric value of 2. 2 divided by the absolute value of 2. This here is another way to denote addition, in fact, plus 1. And then we multiply by the square root of a, and again modulus w, which was the square root of 5. But this time it should be minus a, that is minus 1, and then over 2. Let's just work this out a bit further. So we can take the square root of 5 and divide by 2, and also divide 1 by 2. So this can be written as plus or minus the square root of the square root of 5.
Over 2.5.
And all of this simply becomes plus 1. So plus I times the square root of 5 over 2 minus a half. And here are the solutions combined. Those are the 2 square roots. One is obtained by using the positive exponent, and the other by using the subtraction here, that is, the elevated parentheses. Any questions on this? Maths? Physicist form, yes, and of course you can do that. But in mathematics, we prefer results that just contain the square roots without calculating them out. So it's written exactly. It's correct as is, you could say. We call that exact notation. Any questions? Great. So we've actually finished with the complex square root. And why should we learn that? Well, we actually need to learn it so we can solve complex angular equations. And why do we need to learn to solve complex angular equations? It's because you come across them in oscillation theories in engineering. So you come across a characteristic equation that can have a negative discriminant, and that has physical significance. So if you want to understand that part of Swieninger dealing with negative discriminants, you need to know complex numbers. That's actually why we have it. So let's jump to board number 6. And now let's take a look at what we call the complex attack line. So for those of you taking notes, the headline is the complex line of attack. And a complex line of attack, that's one that can be written like this, some number A. Thank you so much.
Plus some number b times z.
Useland, keep the value of C constant. The numbers A, B, and C, those aren't what you need to find. You'll receive them on the day you're tasked with solving such a different equation, and they could be arbitrarily complex.
So we
B,
can write here that b random numbers from the set of complex numbers.
It's usually said that the one exception is that A cannot be the complex number 0. Because if A was 0, so this whole term cancels out, and then it's not a second degree equation anymore. It becomes a first degree equation. When you need to solve that line, it turns out to be smart to do it the following way.
So you have a sentence.
In mathematics, a theorem is like a structured sentence that describes something, that asserts something, and then you prove it afterwards to be true. So there's a claim associated with the complex quadratic equation. And the claim is, if you're going to solve one, you need to start by calculating a number we refer to as d.
That's proud
The
enough.
discriminant, because this number determines how we should solve it. And you calculate d by saying b squared times c.
Oh, there
And
are
that's
four.
something that once you've done it a few times, you learn it, don't you? Even if you know it from B-level mathematics. The discriminant is b squared minus 4ac. So you start by figuring that out, and then you've got two possibilities. Either d is equal to 0. That's one option. And the other option is that d is different from 0 and becomes a regular complex number. And if d turns out to be exactly 0, it's wonderfully easy to find c. That's the solution. Because what we're looking for here, that is c, the solution to the equation. You just have to state, now you're playing,
In my
they will be
opinion,
starting off with twice a.
so we have the solution.
But it only works if dr is 0. If it isn't 0, then it's some kind of complex number. And then you should be able to find the square root of that, which we just learned how to do. Once you know where to take the square root, you find the two complex numbers that solve for the line of attack by saying negative b plus or minus the square root of the complex number d, using the method we've just learned to find the square root of d, either in polar or rectangular form, and then you divide by 2a. So this is simply the method used to solve complex quadratic equations. It's exactly like the method you're familiar with. The only difference is that when the discriminant is negative, we're no longer in uncharted territory. We can still solve it. So you can say that a complex attack equation always has exactly two solutions. It never has no solutions. It always has precisely two solutions. What do I mean by two solutions? Because it seems there's only one here if the discriminant equals 0. That's correct. There is only a single solution in that case. However, it has what's called a geometric multiplicity of 2. It's a repeated root. Let me explain what I mean by that. I just need to explain the concept of a repeated root.
If you have something that looks like this,
X plus a half, everything squared must equal 0.
So if you were to write this as a standard equation of a line, you'd see that the discriminant is 0.
what it says
It
here.
can be rewritten like this. X plus 1/2 times x plus 1/2. Since x plus a half times x plus a half is the same as x plus a half all squared. And here you can use the zero product property, which states that if this product of this number and that number should equal 0, then either this factor must be 0 or that factor must be 0. And you can see that if this factor has to be 0, then x must be equal to negative 1/2. So that's a solution. And if this factor has to be 0, then x must also be equal to negative 1/2. And that's why we call it a repetitive solution. And you can see it right here. I think I accidentally said geometric multiplicity. It's called algebraic multiplicity too, because it's counted twice, once in each factor. So you actually still think of it as two solutions. It's just the same solution repeated twice. And it's a general rule that any equation of the nth degree has exactly n solutions if you include double roots and if we include the complex ones. This is known as the fundamental theorem of algebra. An nth degree equation always has exactly n solutions. If you count them, it means that you count them multiple times if they are there more than once. And now we'll prove that this is how you solve a complex assault division. And that's what's coming up next, which is really cool and something you've got to get a handle on because it's also part of one of your oral exam questions. So now I'm thinking we'll go through it so we can just take a moment afterwards to practice and see if we can learn it.
So to prove that this is indeed the case, then
you do exactly like you might have done once on Benimo mathematics. You start with the equation and come up with something clever, and that gets you here. Now you just need to be able to explain how to square a complex number. That's the new thing. So we start with another quadratic equation, which says AC squared plus BC plus C equals 0. And you can see this is exactly what you're used to. It's just that there's a C instead of an X. And then we get this brilliant idea to multiply the entire line by 4a, because that's something a mathematician once figured out.
That was clever if you needed to prove this is right.
So I'm multiplying the entire equation by 4a, which means I have to multiply here by 4a, and here, and here, and here too.
Why should I do that? It's proven to be smart.
So I multiply
Again
the
with
whole
4a,
line and I get
and
4.
then b, so
Plus 4ac. Why does it still say 0?
that's because hex 4 is
Tighten
triggered.
the oil. Oh,
This mentions z. Here's something with z. This one doesn't mention z, so I'll toss it to the other side of the dividing line.
so it's going to say 4AEN.
Look again.
Plus 4abz.
It's with minus 4ac.
And then you can see that fora looks a lot like abn minus 4ac. It's just missing just the abn. So that's why it's a good idea to add EBN on both sides of the equation, because then you get the discriminant, the thing that's written over there.
So now there's a new great idea. Put the BN on both sides, just even. So it reads 4a11.
4ABC.
Plus b squared. So now I've added b squared on the left side.
And then I'm just going to put b in the equation on the right side.
There. Now we see that everything on the left side can be written much more concisely because we've learned about what's called the squaring rule. So everything on the left side can be rewritten more cleverly. Let's do that. We rewrite it as the expression 2az plus b squared.
And why does it work?
Yes, because this is the square of a binomial. And to calculate that, you have to take the square of the first term plus the square of the second term plus twice the product. And that squared, what does that give us? It gives us 4s squared. That's what it said, 4s squared. And that squared, that was b squared. It was right there.
I think so too.
And the double product yields 2a's times b times 2. Well, that must precisely give us 4abc. So we can see that everything on the left side can be condensed down to that. And what's written on the right side will simplify to something we'll just call d.
I'm buying the entire right side. D.
Because the number on the right side determines whether that equation has two solutions or a repeated solution, which becomes two solutions again. That's why it's called that. It's a must-have. So the number d discriminates because if d was 0, then it would say, find me a complex number squared that equals 0. There's only one complex number that when squared equals 0, and that's 0 itself. So it's precisely the number 0 that separates the waters here. So now assume that it is 0. Because we don't know it, we assume it. That's how you do math. When there's something you don't know, you make an assumption and think it through under that assumption. So assume that d is equal to 0. If d equals 0, then there's just 0 there. So now it says that 2az plus b squared must be equal to 0. Well then, we know the value inside must be 0, because the only number that results in 0 is 0 itself. So 2az plus b has to equal 0. And now we can simply isolate z. We subtract b from both sides and divide by 2a, and that's how we isolate z. So now we've proven the first point, that z equals negative b divided by 2a, and that's the one solution with algebraic multiplicity of 2, because it's a repeated solution. So that's what you do if d is 0, and that's what we claimed in our theorem here. So now we've proven half the claim. The next half of the claim is almost proven too, because now I will just assume that it's not 0, but different and not 0. But we proceed.
Complex number, and it certainly is.
Why is d a complex number? Well, it's because d is a complex number squared. Minus 4 times a complex number times another complex number. That results in a new complex number. So d is a complex number, and it's not the number 0 now. It's just some complex number we're assuming. But when it says that a certain complex number squared should yield a complex number, then we know there are two solutions, because every complex number that is not 0 has exactly 2 square roots. So that means that it now says that 2 of the given solutions, now we're splitting it up, the second power should give us d, and d is complex. Well, then I know that d here has to be equal to either the plus or minus square root of the complex number. So that means 2a times z plus b becomes either plus or minus the square root of the complex number d. If I want to find c, then I just have to subtract b from both sides and divide by 2a, and then I'm done. So the complex solutions to a complex equation become negative b, plus or minus the complex square root of the complex number negative d,
divided by 2 times the complex number.
and with that we've proven it.
Is that what you do when the discriminant isn't 0?
And I can just run through that one more time without you taking notes at the same time, and then we'll go out and practice it 2 by 2 so you get the hang of it. All right, here comes the story once more, but a bit faster. An equation that can be written in the form a times c squared plus b times c plus c equal to 0 is called a complex attack equation in Z if a, b, and c are complex numbers with the restriction that a cannot be the complex number 0, because then it's not an attack equation. And then the first term would cancel out because it would be multiplied by 0. To solve such an equation, you first compute the number d by taking the complex number b squared minus 4 times the complex number a times the complex number c. If this complex number turns out to be 0, then it's a very simple complex number, which is equal to the real number 0. And then you find the solution by saying that there is only one, but it has an algebraic multiplicity of 2 because it's a repeated root, which means that this can be rewritten into a structure that looks like this.
And right here it just says z, and here's some number or another.
And then one finds the single solution, which is to say negative, the complex number b divided by 2 times the complex number a. The next thing we claim is that if d is not 0, but is some arbitrary complex number, then this equation has 2 solutions, and the 2 complex solutions are found by plugging into this formula, negative b plus or minus the square root of d all over 2a. And to prove that, so we begin with the equation. Step 1, multiply throughout by 4a. Boom. Why? It's clever.
Someone has figured out why it's clever for Sarkomsky.
It can be rewritten as the square of a binomial expression, making it much easier to solve for z. Notice that c appears here and there, but in just a moment, z will be in one place only. And this makes it easier to find c, which is the clever part, and that's why we do it. After we multiply through by 4a, we then take the constant term and move it to the other side. And see, it resembles part of the discriminant. That's a way to remember it when you're taking an exam. It's just missing b squared. So next step, put the br on both sides of these marks. Discuss the right-hand side for d, which is short for discriminant, because this number determines which situation we're in. Rewrite the left side as the square of a binomial. Assume then what you don't know, because you don't know what the number is, so just assume it. And think it through, assuming that assumption. The only other thing that could be true is the assumption, and perfectly finished before that number. And there you have it. And you need to practice it a bit if you want to be able to explain it neatly.
So we're pausing right here, mate, and then we'll take the time to...
Congratulations on your workout. It's easy.
Yes, so we've been out practicing a bit on how to deal with assailants. And just so I remember to tell you, your first mandatory homework assignment will be prepared over the weekend and posted on It's Learning.
And then I'll give it a week's time.
That's something to work on. Is it enough? Are you guys under a lot of pressure right now? A week and a half, a week and a half. Okay, so the last item on the agenda for today.
Maths formula. So here it comes.
Let's take a look at the MOPS formula and what it's about and what it can be used for. And often, when math geeks get really excited about something, it's because it has practical uses. Usually, it's just some other math that can also be utilized. I'll show you some applications of the MOPS formula And these applications are just more math. But if you've worked with integrals, you almost can't help but get a little thrilled by it.
So that's table 7 set.
We've already seen that a complex number can be referred to as a point in the two-dimensional complex plane.
And the headline now, it's MOVs.
And how do we get to there? Well, we begin again by looking at a complex number that lies in the complex plane.
So here's a version of the graph plan.
And here we have a point somewhere in the complex plane where each point is associated with a complex number. So that's a complex number lying there, Z.
And we can write that in the form of A
plus I times B, where B is out here. And then we've learned that if you measure the distance from a record,
Head to set.
and then we get R, where R is the radius of the circle that this number lies on, if the circle has its center in yesterday's coordinates. Thus, R corresponds to saying the modulus of Z. And then we've learned that if there's an angle here, it's what we call an argument from C, and I call it theta. We've learned that if this were a length, then this down here would be the cosine of the angle length. And we've learned that if that one were a length, then this would be the sine of the angle length. But this one isn't necessarily a length, it's R long. So it's not just cosine here, it's multiplied by more than cosine. So the distance that we have here is multiplied by the cosine.
longer than 1.
The distance here is R times the cosine of the angle. Remember that this is the adjacent side, and adjacent rhymes with cos. So here you multiply by cosine, and up here you multiply by sine. So here we have R times the sine of theta. And that means the complex number C, which we had up there, can now be written, instead of writing A plus I times B, instead of that, we can now write it as R times the cosine of theta.
Because this is a different way to write A.
And that was the distance, which was a plus I times B, but B was R times the sine of theta. And there we can see that R was a common factor, so we can factor it out into a large parenthesis here. And what remains is cosine of theta plus I times the sine of theta,
Cosmos theta.
plus I times the sine of theta. And this, it represents a complex number in what we call its polar form, where you can read the angle directly. But as we've learned, this can also be written as R times Euler's number raised to the power of I times theta. We haven't proven that step yet. That's the big reveal at the very end of the course. So for now, we'll just
Cosmos
accept that theta plus I times theta.
Sin theta can be proven to yield e to the power of theta.
And this formula is so important that it has its own name. It's called Euler's formula. So that's the first thing we need to understand.
Having just learned about it, I'd probably say right now that Euler's formula states
that raising e to the power of the imaginary unit times an angle theta is equal to the cosine of this angle theta plus the imaginary unit times the sine of this angle theta.
this is Euler's formula.
And from that, you immediately get to the headline as if it were the MOFS formula. Because what you do now is you say, given what I get, if I take E
In the seat and uplifting, you ended it.
well, if I raise this to the nth power, then it should be equivalent to raising that to the nth power, because I believe that the two are equal, even though I haven't proven it yet. So this is the same as writing cosine of theta plus I times the sine of theta.
And then
By
sit.
the way, that's all. But it turns out that even when dealing with the complex exponential function, so we can still multiply exponents. That's really wonderful. The rules we know from the laws of exponents still apply, so I can multiply by n down here. So this can also be written like this.
E to the power of I times theta equals E to the power of I times negative theta.
And I just have to walk right into it.
And what comes after the I? That's my angle.
So what was written here, it was e raised to the power of I times some angle. What is that? It's the cosine of the angle plus I times the sine of the angle. So e to the power of I times this angle must be equal to cosine for the angle which is in theta. And I times the sine of the angle in theta. So that means if this equals that, but that also equals this, which equals that, then this must equal that.
That right there, that's the Morse form.
So the formula looks like this: the cosine of an angle and times the sine of this angle.
Everything eventually came to an end.
Is exactly the same as cosine times the angle plus I times the sine of the angle.
So here it is.
And it turns out that this formula can be used for all sorts of cool things.
Let's try to give an example of what some of the cool stuff is.
So here comes an example on how to use them when heated up. For example, 1. Imagine I pick n as 2. It was a relatively modest choice. 2 is such a nice whole number that isn't too big. That means if I plug in 2 there and work out what it gives, it should be something I can compare to this over here. That way, I might get some results that can be used for something. Let's try that once. So if I now put n as 2, it would read cosine of theta plus I times sine theta. All of that squared.
I've decided it's 2 p.m. now.
What would that be exactly? Yeah, it should match this over here.
So I really wanted to give cosinus to 2 theta plus I times the sine of 2 theta. But we can calculate this, and it's the square of a binomial expression. And squaring a binomial gives us the square of the first term plus the square of the second term plus or minus twice the product. In this case, plus twice the product because there's a plus sign. So let's continue calculating on the left side using algebra.
So on the left side, what does it say there?
It's an abbreviation for the left-hand side, that LHS. On the left-hand side, we have the square of the first term. It's cosine of theta squared, where one decides that maybe they'd like to sort of do this thing where they just move the squared right after the cosine. So I will take the square of the second term, but we must remember that both I squared and sine squared must be considered, and I squared equals -1.
And finally, I end up getting twice the product.
With the double product, that gives 2 times cosine of theta times sine of theta, all multiplied by I. So I can try to write that here, plus I times 2 times cos theta times sin theta. That's what I get if I work out the left side here.
But it still has to be the ones on the right side.
I just tell them to respond with that. So all of this needs to be compared to the right-hand side. And what did it say on the right side? It said cosine of 2 theta. Cosine of 2 theta plus I times sine of 2 theta. And now we can compare, because if two complex numbers are equal to each other, so they should have the same real parts.
And this is everything that helps you in Greenland. And that's the genuine article, because there's nothing inside.
And they must have the same imaginary part. And this is the entire imaginary part. And this is the entire imaginary part. They must also be equal.
So now I can draw a conclusion.
And here's my conclusion.
We are concluding
Through
now.
the use of complex numbers, we now conclude something completely real. Something that doesn't have anything to do with complex numbers, but we have explained it using complex numbers. What do we conclude? The cosine of an angle minus the sine of the same angle is equal to the cosine of double that angle. Because the real part has to match the real part, this complex number cannot be equal to that complex number. So if this complex number equals that complex number, then the real part must equal the real part, and the imaginary part must equal the imaginary part. Therefore, we can state that cos 2 is equal to cos 2. It's the same as cosine of 2 times theta, negative sine of the coangle. And this is an entirely ordinary real result, but we have proven it using complex numbers. There's absolutely nothing with I in this at all. And at the same time, I can say that the sine of the double angle is 0. Equals 2 times the cosine of the angle. Twice the sine of the angle. In English, these are called the double angle formulas from trigonometry. So there are 2 trigonometric identities that apply to ordinary numbers, but they are super easy to prove using complex numbers. And then you might be wondering, what's the use of all this? Well, I'm about to wrap this up by showing on the next board exactly what you can use it for. Sometimes integrals pop up where you have to integrate the square of the sine function.
You can do that using these paraphrases. All right, let's give it one last try for today. All right, then it's going to be board 8. And I think I'll just let the conclusion stand and erase the rest here.
Let's take a closer look at this formula here. Let's say we call this one number 1 and that one number 2. So formula 1, let's show where one could apply it. It states that the cosine of the double angle 2 theta is the same as cosine squared of theta minus sine squared of theta is the same as cosine of 2 theta minus sine of 2 theta. And do we know anything else about sine of 2 and cosine of 2? All right, there was something called the idiot formula from high school level math. Do you remember the fundamental relation? Looking at the unit circle, I reminded you guys a few weeks ago that indeed, if you look here at the unit circle
and an angle theta.
So here we have cosine theta and here sine theta. And this side is 1. So if I just blow up this triangle a bit, then it looks like this. Here's 1 here of the cognitive activities. Here is sine theta. And here is 90 degrees, which makes this a right angled triangle. So Pythagoras' theorem applies. And since Pythagoras' theorem works, this squared plus this squared must equal that squared. So the cosine squared of an angle plus the sine squared of the same angle must equal 1 square, which is 1. And that is what we call the fundamental relationship, what I'm writing down now. The cosine function of an angle, the sine function of an angle. And it must be the same angle. It always equals 1. But that means that I can isolate the cos brane here if I feel like it. The cosine of theta, how can I write that? Well, I can write it as 1 minus the sine squared. Minus the sine squared. Thank you very much. And if I take this here and stand here and plug it into the square of cosine at the top and continue with the fraction on line 1. So it reads cosine of the double angle equals cosine of theta, but it's the same as 1 minus sine of theta. So this right here is cosine brane in disguise. And from there, I should subtract the sine brane. So that's what we have then. Well, then we have that cosine squared to 1 power equals 1 minus 2 times the sine of the exponentials. So I could actually just subtract 1 from the back of the equality sign and divide by -2. So that's how I find sine squared. Okay, let's give that a try. So if I say sine squared, so what's that about? So it must be equal to, again, minus the cosine at hjørnet. That's 2 tasks.
And that brings us down to 2. Isn't that right?
If it turns out negative, then it becomes positive 1/2. And if it's already positive, then it turns into negative. And this I can rewrite as 1/2 minus 1/2 times the cosine of 2 theta. And this whole thing might seem like a big intricate pattern of math. What's he doing? What's this all about? Well, look, I've rewritten sine squared into an angle. 1/2 minus 1/2 cosine of the double angle. And why is that clever? It's clever because if you even come across this integral here, and it pops up in a real world application, this integral right here, the integral of sine squared. So you just take it in stride. And that's the integral right there. But then you just do this clever thing, where instead of writing sine squared, you write that. And you don't get cold feet with it because it's easy to integrate. So this integral is expressed as
much.
What's that? It's a whole
minus 1/2 times the cosine of 2 theta. And then we just get started with the integration. Now it's straight down the road. Because we've learned that when you need to integrate multiple terms, you do it term by term. What's the antiderivative of 1/2? It's 1/2 times x. But now it's not x, it's 1/2 theta. And then I need to find the antiderivative involving cosine. What gives us cosine? The derivative of sine gives us cosine, but I need a negative, so it must be negative sine. So that's going to be something with negative sine to the double angle. But if I differentiate that, it'll get multiplied by 2. So I need to remember to divide by the derivative of the inside function, which means if I divide 1/2 by 2, I get a quarter. Quarter is I assert that if you differentiate this, you'll end up with that. Let's give it a try. Negative 1/4 remains when you differentiate. The derivative of sine results in the cosine of the same angle, but remember to multiply by the derivative of the inside, which yields 2. 2 times 1/4 equals 1/2, and there you have it. 1/2, and there it is, plus a constant. The invention of complex numbers extends far into the real world. All sorts of problems in mathematics that we couldn't solve before can suddenly be solved because we invented complex numbers. Because all sorts of results emerge that we might never have discovered if we hadn't come up with complex numbers. But what's so cool about complex numbers is that they take us to a whole new level of abstraction, almost into a world of fantasy. Yet it turns out our real world has borrowed from that very concept. There are things in the real world that can be explained with complex numbers. And if we had never figured out how to explain them, we wouldn't have invented them. We would have had to invent them. That's probably enough of the sermon for today. Have a good weekend.